Greetings and welcome to this third or fourth video, depending on how you look at it, in our series regarding a can crusher and the analysis of a column. In the last video, we looked at this column as if it were made of 2014 0 aluminum alloy, and we found out that it was going to not support the load that we needed before it buckled, well, at least within our design factor that we were hoping for. So I'd like to show you a little bit better what I was talking about when it comes to the different failure modes. So if this were to buckle in the X direction, it would bow out like this. Notice how it's supported here and here at pins, but no other supporting would be available to it. But it could freely rotate here and here, which means that it would have complete freedom in those two locations to rotate. If it were to buckle in the Y direction, this is what I'm talking about. It would bow out here, but up in this region here, it's being held in place fairly well by this pin. And showing a gap here just to see how it's put together, but I would suspect that I would assemble it so that it was held in place a little bit better anyway. But this is what's meant by the fixed in this direction. So it's fixed down here and won't be able to move because it's held by that pin, so it won't be able to rotate as it does in the XX. So that changes our fixity factor K. So here's the original analysis that we did, and we found that in X, it was strong enough. It could take 806 newtons, which is greater than the 450 that we wanted. But in the Y direction, even with that fixity factor of 0.65, it was only able to handle 238 newtons for an allowable load. So we decided that it was time to redesign it. So here we are back at our work page, and we're going to start over with a column redesign. Now I'm going to change a few things, so let's go to our givens. Okay, we still have our required load of 450 newtons, but now we're going to say that our new material is 1040 hot rolled steel. And another one is that we want to make this particularly inexpensive, so we're going to get some standard sized steel for this, and it can come in strips that are an inch wide. Now I know we were using millimeters, so we're going to say that 1 inch wide is 25.4 millimeters. So that means I'm going to cross this out and make it 25.4 millimeters. So that's going to make that much larger, but this should be able to work with it. And then the question is, what's this going to be? So that's actually what we're going to work on finding. The minimum height. So I want the smallest height that we need to make this cross-section work in this material. So a lot of the things beyond this are going to be the same, but we're going to have to look some stuff up. So Gonna look up for the material we have from mattweb.com, and this is 1040 steel as rolled. We'll use these values. Ultimate strength of 620, yield strength of 415 megapascals, and a modulus of elasticity of 200 gigapascals. Now, we haven't used the ultimate strength yet, but it's sometimes just good to write some extra things down that you think you might need. Okay, and we won't make the same mistake we made last time. We'll use the gigapascals that we were supposed to use. Okay, so from there, we're going to calculate our column constant. And that is the same formula as we had before. 2 pi squared E over the yield strength all under the square root symbol, 200 gigapascals over 415 megapascals. Again, a gigapascal is 1,000 megapascals, so just throw the 1,000 in on the top there, and we end up with a CC column constant of 97.5. So again, if the slenderness ratio is above this, it is slender or long, and if it is below this, then it's intermediate. So again, we're going to look at this from two different perspectives. One is buckling failure in the x direction, and then we'll, after that, consider it in the y direction. So in the x direction, we have pinned, which means our k equals 1.0. Again, looking at buckling modes, here we have pinned, 1.0 is what we use. And we need to calculate our slenderness ratio, which is a function of the radius of gyration, which is a function of the area moment of inertia and the area. So we have to calculate those first. So if buckling failure is in the x direction, like this, then it's about the y axis. So we calculate IY, and remember 25.4 is our base, and we don't know what our height is, so we'll just use h for that. Yes, this complicates the problem somewhat. In fact, this is something I really want to focus on here, is that we're trying to find the minimum h. We don't know what it is, so we're going to have to use that as a variable all the way through. So I hope you can follow this with me. Okay, so IY is going to be HB cubed over 12. And the area is going to be base times height. So our y is going to be the square root of IY over the area. IY is HB cubed over 12. And area is BH. Now the B's cancel out. Well, I've got 3 B's up here, and I'm down to 2. The H's cancel out completely. So I'm left with RY equals the square root of, okay, I had 2 B's on top, So b squared over 12. And that means if I can take the square root of the top and the square root of the bottom, then the square root of b squared is simply b over square root of 12. Oh, we are actually given b, 25.4 millimeters. All over the square root of 12, and we get 7.33 millimeters. And that's our RY. So it doesn't matter at all what our H was in order to find our radius of gyration in the Y direction. Okay. Now we can plug that in and get our slenderness ratio. Slenderness ratio is KL over R. K, as we found out, is 1.0. L comes from the other problem, and it's one of those givens, 200 millimeters. And that goes over R, which is 7.33 millimeters. So our slenderness ratio comes out to be 27.3. 27.3 is definitely less than 97.5, which is our column constant. So we definitely are in the intermediate realm, which means we use the JB Johnson method. That says that the critical load is the yield strength multiplied by, again I call it a mass because that's kind of what it is, 1 minus this fraction, the yield strength times the slenderness ratio squared all over 4 pi squared times modulus of elasticity times the area. Now we are going to set this critical load equal to our required load times our design factor. So what I'm saying here is that our required load, this is what we expect it to take. If you go this much times that, multiples of this value, then it's going to get to this critical load where it's going to collapse. We had from the previous part of the problem n equals 4. So what I'm going to do though is I'm going to rearrange all this stuff using variables, because if we write it all out it can get messier than we need it to be. What I really want to do is I want to pull out the area here because we don't know it. That's exactly the point, is that we don't know h. We are trying to find that, and h is used to calculate the area. So I'm going to separate this out. Area equals base times height, and that equals, I just need to take all of this stuff here divide both sides by this much, and then I'm going to get my area. So base times height equals the required load times our design factor all over this big old mess of the yield strength times 1 minus the yield strength times the slenderness ratio squared, all of that over 4 pi squared e And again, the area we already have over here on the left-hand side. So if I know B, which I do, I'm going to divide both sides by B, and B is down on the denominator here. Okay, now I can plug in all of my values. Our required load is 450 newtons. Design factor is 4. Yield strength is 415 megapascals. And that again, 415 megapascals. Our slenderness ratio is right up here, 27.3. Square that and divide that by 4 pi squared times 200 gigapascals. And finally, that whole denominator still has to be multiplied by B, which is 25.4 millimeters. And that gives us a minimum H of 0.178 millimeters, which when you think about it, that's pretty small. That makes a lot of sense because we are so wide in this fashion. But if we make it this small, I'll bet a whole lot of money that we are going to fail in the other direction. So not so fast on this answer. Okay, one more thing about the units here is that we have units of newtons over megapascal millimeters. Now a megapascal times a millimeter squared is a newton. But so this is megapascal times millimeters. So this is going to be Newton per millimeter, but that would make it on the bottom, so the millimeter comes up on top. Newtons cancel out, so we end up with just millimeters. Okay, what happens if we have buckling failure in the y direction? Well, we're assuming it's fixed, so K equals 0.65, and we will start with area moment of inertia in the x direction is BH cubed over 12, and again our area is B times H. We're going to keep these in variable form for the moment. So R in the x, square root of IX over A equals the square root of BH cubed over 12 all over B times H. And the B's cancel out. This H cubed becomes H squared because it cancels one of the H's out with that one. And we end up with square root of H squared over 12. And this becomes the square root of H squared. It's going to be H. And we got on the bottom the square root of 12. Well, last time it was easy because we already had B given to us, 25.4 millimeters. But this time we have H, and H is what we're trying to find. So we can't calculate this yet. So I'm going to have to continue on using variables and see what happens. So we're going to work with the slenderness ratio, which is KL over R. K is 0.65, L is 200 millimeters. R is h over the square root of 12. So if you put this stuff into a calculator, you end up with 450.3 over h. And this will, since we've only been using millimeters, this will come out to millimeters. But this isn't very helpful when we're trying to figure out if we should use the JB Johnson or if we should use the Euler method. Now, considering the last time we had 3 millimeters here, it ended up being fairly substantially in the long zone, in the Euler zone. So we're going to assume that this is going to stay in the Euler zone. So, I mean, if you look at this, we only had 0.2 millimeters here. So it's going to be thin, and therefore it's going to be slender, and therefore we're going to use Euler. Okay, so we're going to assume that it's long. And we use the Euler method. So the critical load can be calculated using pi squared EA over SR squared. Now, remember that A and SR are both functions of H. So this is going to complicate things. So I'm going to continue using variables for a little bit. Now, again, like we did over here, we're going to set the critical load equal to the required force times the design factor. Now, let's solve for that required height. The things that are functions of H are A and SR squared. So I'm going to separate those out. Pi squared E times B times H all over KL over R is H over square root of 12. And that gets squared. And then there are no H's over on the right-hand side. So then I'm going to divide both sides by everything that's not H. So that includes pi squared EB over, well, on the bottom is KL squared, and the square root of 12 is on the bottom, but it gets squared, so it multiplies by 12. So we have pi squared EB over 12 times KL quantity squared. Okay, so that makes things a little bit better because I now have, and the H was on the bottom and it's squared. So that means there are two H's that are coming back on top and then one H up here. So on the left-hand side, I just have H cubed. On the right-hand side, I have, so the 12 KL squared is on the bottom, so I have P required times N times 12 times KL squared all over pi squared E times B. Now we can plug this in. H cubed equals P required 450 newtons times N, which is 4, times 12 times K is 0.65, L is 200 millimeters, so there's some units here, all over pi squared times 200 gigapascals. You know what, I'm going to undo that and call it 200,000 megapascals times B, and B is 25.4 millimeters. So on top I've got Newton times square millimeters. On the bottom I've got megapascals, which is a Newton per square millimeter, so the newtons cancel out. On top we'll have millimeters to the fourth. On the bottom we'll have millimeters, so we'll have millimeters cubed. So h cubed equals 7.28 cubic millimeters, and then if you take the cube root of that, h equals 1.938 millimeters. Oof. Well, that was some rough algebra, but we made it through. So I have a proposed minimum h of 1.94 millimeters, and that's a stark contrast to what we got for the other buckling direction. So obviously it's going to be much more likely to fail in this direction. Now we have a couple things that we still need to do here. First off, I want to pick something out that is a little bit more economical than telling someone that we need 1.938 millimeter thick steel. They don't usually sell it in those kind of random configurations. So what we can do is go to our local supplier and see what's available. Now, this might not be from a supplier, but it does give you the different values for the different gauges. So often this type of steel is going to be produced in sheets. Sheets are known by their gauge numbers. So look down the list here, and the approximate thickness in decimals for an inch is here, and in millimeters it's here. So we want to look for something a little bit larger than 1.94 millimeters, and this looks just about right. This is 14 gauge steel, right around 2 millimeters thick. So we're going to go with that. 14 gauge sheet with a thickness of 1.984375 millimeters. Okay, there's too many decimal places, but even if we went with 1.984, we'd be just fine. Okay, so we should calculate our slenderness ratio to check that our assumption was correct, but we'll have to calculate our area and our I and so on first. So I equals BH cubed over 12, and we end up with 16.5 millimeters to the fourth. Area is base times height. That gives us 50.4 square millimeters, and that means our radius of gyration around the x is the square root of that over that, and we end up with 0.57 millimeters, and our slenderness ratio is 226.9, and so then it is correct. Our slenderness ratio is greater than our column constant, so we use Euler. Now, quick note is that the AISC says you probably shouldn't use anything with a slenderness ratio of larger than 200. But that's with large structures and so on, where there's a lot of safety involved. Maybe your average can crusher, it's not so important. But that's just a side note there. All right, now that we have our slenderness ratio, we have a dimension picked out, let us find out what our critical load actually is. Critical load is pi squared EA over SR squared, and that's pi squared times 200,000 megapascals times our area, which is 50.4 millimeters squared, and divide that by our SR squared, which is 226.9 squared, and you get 1,932 newtons. Okay, now we want to compare that to what we were hoping for, and we have our allowable load equal to our critical force divided by N, and that is 1932 newtons divided by 4, which gives us 483 newtons, which is greater than our 450 newtons, so it checks out. And so it is okay that we go with 14 gauge sheet steel, and we should achieve all of our objectives. So to recap this problem, we started off with a can crusher design. We wanted to know what the force was on this member and whether it would stand up with our present design. Now, we determined that we might have a failure mode like this, buckling in the Y direction, or it might buckle out like that in the X direction. So that was part of what we had to figure out. Well, we did figure it out with our initial design of an aluminum bar like this, but it did not come up to the level of what we needed. We were hoping for a required force of 450 newtons, and we wanted to have a design factor of 4. So 4 times this is where we would have expected it to fail and collapse, but we found that it was going to buckle before that point. So we decided to do a redesign here using steel, and relatively low cost steel, and we figured that 1 inch wide is very common. We just didn't know what thickness we were going to pick out. So that's what we wanted to do. We wanted to find the minimum thickness. Well, for the steel, we needed to calculate the column constant again, which is again based on material properties. And then we looked at it in X, and we went back through, and we again said it was pin, so our K is 1.0. Well, we couldn't calculate the I and the R and the SR right away because we didn't know what this value H was. So we just used variables and kept it with variables all the way through until the very end where we could solve for H, because the only spot we had H was with this area here. We got to a very small number, so this is very strong in the X direction. Didn't need much to hold it in place, but that also indicates that we're probably, we may very well be weak in the Y direction. So we went through and we did basically the same thing, and we assumed it was going to be long in the Euler. In other words, pretty flimsy and slender, so it was going to fail because of its length. So we use the Euler formula here, and again kept it with variables. And this was more complicated because we had to get h cubed out of here, but it was able to be done. Everything else we could plug and chug, just a lot of that right there. And we took the cube root and found that the minimum thickness was almost 2 millimeters, which is very different than the other one. So it definitely would have failed in Y, because we needed at least this for it not to fail in Y, and something this thin would certainly have collapsed pretty quickly. So we looked on our gauge sheet and found that 14 gauge is a little bit more than this, and so we just chose that and then plugged it back in to calculate all these things again. And we used the Euler method because we found that the slenderness ratio was definitely much larger than the column constant. So we used the Euler method and plugged all those in, making sure we followed the units properly, and we ended up with a critical load of almost 2,000 newtons. After that, we calculated our allowable load, which ends up being 483 newtons after dividing by the design factor. And considering we were shooting for 450 newtons at a minimum, we were able to achieve our goal. So this was a good choice for us. Well, I hope that this series of videos has helped you understand column analysis and design a lot better. And thanks for tuning in. Good luck with your studies.